Welcome back, everybody. So we're covering the next couple of sections in chapter 23, all about organometallic compounds. So now we're reviewing some material we had seen before, and that has to do with dialkyl cuprates. So we have copper inserted into our carbon compounds. The given reagents are formed by reacting an organolithium compound with cuprous halide. So remember, we used a halide made in organolithium, and now we're focusing on the second step. We need a 2-to-1 ratio, so therefore a 0.5 equivalent of our copper X component, and we now have two alkyl groups present in this Gilman reagent. Very important though, please remember that even though there are two R groups present, that only one R group is being transferred into a substrate. Let's look at a couple of examples. So we can now actually make Gilman reagents by using alkyl, vinyl, and aryl components. The primary halides work best in here as it prevents side reactions. We need to use two equivalents to make the organolithium compounds that is then being converted into the cuprate, and we incorporate twice what is shown here in red, the alkyl or aryl or vinyl group into our cuprate structure. Again, only one of the red groups is going to transfer in as we're looking at reactions. The next slide has a review where the Gilman reagent has been mentioned before. So when looking at these lithium dialkyl cuprates, we had seen that acid chlorides can be reacted, and here we only have one transfer of an R group, and you can read through the details here as well. This was discussed in chapter 20. And we also had noted early on in one of the slides that because this is a different kind of nucleophile, it's less reactive than the Grignard reagent, that this prefers a 1,4 addition. Remember, we count from oxygen 1, then 2, then 3, and 4. This is also referred to as the beta component, and we see this with alpha-beta unsaturated carbonyl compounds, such as this ketone shown here. So this is referred to as a 1,4 addition, as we only get the addition of an R group in the 4 position, and we should probably make an adjustment so you can see the two methyl groups here are shown here, and this is your new bond that has formed on the beta carbon. Moving on, we want to learn a little bit more here. We can refer to these reactions actually as coupling reactions. You have color coding seen here. Again, the cuprate itself, because the cuprate itself, here we have a red R group. Only one of the R groups is now merged with whatever the halide was that was being used in the beginning. So we're making a new coupling product, and we're less concerned with the side products that are being formed here. Now, because we can do these coupling reactions, there's this named reaction. This is referred to as the Corey-Posner Whitesides-House reaction. And we also should make a note of the fact that when we are trying to do these coupling reactions, we typically have low temperature because these components are quite reactive, and we need to use an ether, such as diethyl ether or THF, so a non-protic solvent, in order to have good selectivity in these transformations. Okay, so here a little bit more detail. As we're looking at the cuprate and the halide that's being brought together, this works best with methyl and primary halides, as well as vinyl and aryl halides. So it can be CH3 hybridized, sp3 hybridized or sp2 hybridized. And we are replacing the halide overall with one of the R groups from the organocuprate. Please also remember that when we have halides that are secondary or tertiary, we will get side products, so we want to avoid that. So we stick with methyl, primary, aryl, and vinyl halides for successful transformations in the Corey-Posner Whitesides-House reaction. We also want to understand and make a note of the fact that this is a stereospecific reaction, which means that the stereochemistry contained, let's say, in a double bond is retained. We have here an E arrangement, an E alkene and a Z alkene. And as you see, of one of the red portions being transferred to replace the iodide, we now have the E as well as the Z stereochemistry retained. So we say that this reaction is stereospecific because we don't see any of the other isomers. The mechanism is more complex and beyond the scope of this class. But the other really intriguing aspect for using this gamma reagent is that it's compatible with many functional groups, and that includes ketos, esters, and amide groups, so we can build bigger molecules and not be concerned about ketones, esters, and amide groups in here. What you see again in this example on the bottom is that one of the phenyl groups is taking the position of the iodine, and the stereochemistry, which is trans or E, is being retained. So coupling allows us to make new carbon-carbon bonds, R prime bonds from two organohalides. Remember that these arrows here are retrosynthetic arrows. So we're going back as we're trying to design the synthesis. We can generate both the halide as well as the organocuprate reagent. We can generate the organocuprate reagent also from a halide. We just have to modify the R groups. So as we're looking for the forward synthesis, and here now we see that all we do is we treat an organohalide, make the organolithium, then we prepare the cuprate, and then we take another organohalide to now get the coupling product. And I encourage you to practice some more examples in the skill builder section. And in this last section of chapter 23, we're discussing here a few things about a named reaction, that is the Simmons-Smith reaction. We're now dealing with organozinc compounds, and they react very similarly to Grignard reagents in terms of the overall conversion. Remember that we had used organohalides to now insert the magnesium into the carbon halide bond. And the important component here was that we have a very strong nucleophile because we changed the bond polarization. We went from a delta plus and delta minus to, and now a delta minus strong nucleophile for R dot dot minus. We have delta plus magnesium, and then we have delta minus for the halide. Because the carbon-zinc bond is not as polar as the carbon-magnesium bond, because zinc resides further to the right in the periodic table, the carbon atom is only giving it a partial negative charge, while we had said with the Grignard reagent we can think about this as an R dot dot minus. So that is a distinct difference, which means that these organozinc reagents are more selective. They're less reactive and more selective. But there's really a variation of using organozinc compounds that's described in the Simmons-Smith reaction. This is referred to as a cyclopropanation reaction, meaning that you're making a cyclopropane ring in this reaction. The reagent that's being utilized is ICH2 zinc I. So this organozinc compound forms when a zinc copper couple, also shown as a zinc-Cu. This happens when we treat zinc dust with copper sources. It's an activated zinc in that case, making more reactive. When we are using CH2I2, so diiodomethane, we can actually now generate a source of a methylene group, which is a CH2 group. So basically we are transferring this component here. And it is very similar to reacting with a carbene. So the parallels are very, very similar. And when we see this iodomethyl zinc iodide, we should think about this CH2 group now delivering a carbene unit as drawn here. What's unusual about carbenes is that it's an overall neutral molecule in which a carbon atom is surrounded by only 6 valence electrons, 1, 2, 3, 4. On the next slide, we have some more information. Again, here is the Simmons-Smith reagent, and it can be seen as acting as a nucleophile and an electrophile. Again, we want to think about a carbenoid reactivity, whereby this electron pair is helping to form a bond to the carbon of an alkene unit, while the pi bond is helping to make the second bond. We can also utilize this structure, the Simmons-Smith reagent, to draw 3 arrows, and you see that zinc iodide is a side product in here. But here is your cyclopropane ring, and we also see that the stereochemistry of the double bond is being retained. So we want to make a note of this also being stereospecific. If we have a trans double bond, it means that in the cyclopropane they will end up on opposite sides, and you will also form the mirror image known as the enantiomer. Just remember that this is basically a delivery vehicle for transferring a CH2 group. So you're making a new bond. Here's your CH2 group, and you're forming now the cyclopropane unit. If we have a cis alkene, we will see now that the 2 substituents are on the same side. There's no enantiomer to this because it's really symmetrical. Remember that we have symmetry here, so that this is actually a meso compound. It is achiral. Here are some more examples. I recommend you pause the video, you jot down the examples, and just draw the structure. The solutions will be shown on the next slide. And here you are. You are converting each alkene into cyclopropane. Here the cis double bond means that the cyclopropane can only accommodate to be on the same side. And then here we also have a cyclopropane being formed from the alkene unit. Here there is no stereochemistry. Other cyclopropanation reactions can be achieved by using a different carbene. This carbene, instead of 2 hydrogens, has 2 chlorine atoms. It turns out that this is far more stable and that these reactions are more readily achieved. We can make this dichloro carbine from chloroform, so a common solvent. Basically, there's an overall elimination of a molecule of HCl. First, a proton is being abstracted by the treatment with a strong base, as you can see here, and then the chlorine atom is a very good leaving group, and you form the dichlorocarbene. Again, this carbene functions both as electrophile and nucleophile, and now we just have 2 arrows shown here as opposed to what we saw with the organozinc component. But again, we're making a cyclopropane ring as shown here. Now we have 2 chlorine atoms instead of hydrogen compared to the previous reaction. So basically we're effectively adding a methylene group, so either CH2 or CCl2 across a double bond, which is shown here. When you see these conditions, a strong base and chloroform, this could be any kind of CHX3, from which we eliminate HX, you form the carbene. So understand that this is a delivery vehicle for X, X, and then carbene, dot, dot. So the next few slides are simply the summaries, in part also shown at the end of your book, your chapter. Review of the reactions. We discussed organolithium as well as organomagnesium compounds. We looked at some of the parallels. We know that we take 2 equivalents of elemental lithium to now make that carbon-lithium bond. Similarly, we had seen many examples where we form a strong nucleophile in a Grignard reagent as shown here. We also revisited the Gilman reaction and looked at a coupling reaction. We can utilize halides. We prefer iodides, bromines, and chlorines, alkyl, aryl, and vinyl, and these should be methyl or primary for the best outcomes to make these organocuperate reactions. Next, we had looked at the coupling reaction, so we're making new bonds. As you see here is your coupling product, a very powerful method for building larger structures. And we had looked at the stereospecificity of these transformations, whereby the stereochemistry, such here the E and the Z stereochemistry, is retained in the product. So there's a large amount of control in these transformations. And then last but not least, we looked at cyclopropionation reactions by either transferring a methylene group, as shown here. The stereochemistry in the double bond is retained as the new three-membered ring is formed, and we had seen the variation whereby we're using a strong base and a CHX3 molecule to now make a cyclopropane with two halides attached.